Okay, welcome back and thanks for tuning in again. So today we're going to pick back up on the old Onan genset here. This is the 140WE 140 kilowatt genset powered by the 884 cubic inch Royal Line V8 engine running on natural gas. So this video is going to focus on the conversion or the electronic governor conversion that we're going to do with this thing. So I've got my parts sitting right here. So let's take a look at them and then we'll go ahead and get started. We got a couple other things to do besides the governor. I want to talk a little bit about the fuel system, but we'll cover that in a little bit. So let's get to it. Okay, well, before we jump into the governor conversion, I want to talk briefly about the status of the engine. So at the end of the last video concerning this unit, we did a test run. The test run lasted about 10 minutes, but at the end of the run, as the unit was stopping, you could clearly hear that we had an exhaust valve leaking. You could hear that chuffing out of the exhaust. So earlier today I went and took compression readings from all 8 cylinders. Everything looks okay except for cylinder 6. Cylinder 6 came in at only 135 pounds compared to, say, cylinder 1 or cylinder 5 or cylinder 7 and 8. They're all pretty good. They're within a couple pounds of each other. Cylinder 4 and cylinder 3 and cylinder 2, they're a little bit weak, but not that bad. But definitely we got a problem at cylinder 6. So I've already pulled the rocker cover on that side and found that sure enough we've got a damaged exhaust valve guide. There's a lot of guide clearance between the valve stem and the inner diameter of the guide. Why that occurred, I don't know. It's a shame that I didn't realize that when I was adjusting the rocker arms a couple months ago, but it is what it is right now. There's nothing I can do about it without pulling the cylinder head, and I don't really want to get into that right now. So I want to install the governor, get the thing running at its correct speed, and we'll see how it does on the load bank. I don't think we can do any more damage to the engine that has already been done as far as that guide is concerned. So let's go into the governor. So here are the main components. We've got the governor controller itself. This is the brains of the operation. The governor actuator here. This is just essentially a big electromagnet, big coil of wire in here with a plunger which acts on this lever right here. There's a little lever with a bearing on it inside this housing. And then when the magnet or the coil is energized by the controller, it pulls the plunger down and rotates the shaft. And then we've got a speed sensor. We refer to this as a magnetic pickup or mag pickup. So really simple. There's a coil of fine stranded wire running through here. There's a magnet at the inner core, which is attached to that little center point there. And this counts flywheel teeth. As the flywheel is rotating, it generates an AC output signal which the governor controller reads, and the frequency of those pulses, each flywheel tooth going by the tip here generates a pulse, and that's just exactly how the governor controller quantifies the engine's speed. So we'll get more into that later once we install it and connect everything up, and we actually go through the procedure of adjusting it. And then we've got the mount for the governor actuator. We got a little base plate, a pedestal, and then this is the blanking plate that I made for the mechanical governor that the engine used to have. So let's take a look at the engine and see how this is going to mount up. We'll start with the actuator. Before we get started, I want to say that these components are pretty much industry standard governor components. They're a little bit outdated now. These are all probably 20 years old. These are all second-hand parts that I've had laying around. This one, the actuator obviously came off of a Kohler gen set. I don't know what type, but that beige color gives it away. You know, Barber Coleman controllers are used on pretty much every make and model of generator back 20 years ago. And then mag pickups, same thing. Generators still use mag pickup just like that nowadays. So nothing new, nothing revolutionary here. So, but if you were creative, you could build all this equipment yourself. You could build your own governor controller, your own electronic controller. You could build your own actuator, and you could you don't even have to use a mag pickup. You could either build a mag pickup, or your controller could read AC output frequency from the generator end, or it could take a signal from a distributor. You wouldn't want to use an alternator tach output, because if you had any belt slippage, that could give you a false speed reading. Over here at the engine, some of you may remember that this here is where the original mechanical governor bolted. This is an aluminum plug that I made to plug up the oil passage that would have fed the original governor. So I've got a blank off plate, or blanking plate, that I made here. That's going to sit right there like that. I've got a little piece of, this is what, 1 inch by 2 inch by 1/8 inch wall rectangular tubing. Plan is to weld that on there. Weld a mounting plate or a base plate for the governor actuator. Something like that. And have the actuator itself bolt on right there. Kind of a big, imposing thing on the engine. I was hoping I could kind of sit this down lower, but right now I think to get the best geometry between the actuator's lever and the throttle lever, this is going to be the best location installation, or installation location. So one other thing I did off camera is I made this lever arm here for the throttle. Originally the mechanical governor bolted on, or the linkage bolted on right here. This little cast piece is original. I made up this lever with these multiple holes in it to be able to bolt on here to give me more options for connecting the mechanical governor. There's a little bit of an art form to setting up the linkage here to get the correct rate of travel in the governor or in the actuator to the correct rate of travel for the butterflies here, the throttle butterfly, especially on a gas unit like this, because the fueling for, or the throttle operation for butterfly valve it's not quite linear. So you've got a greater rate of change between, say, 30% throttle and 100% throttle than you do at, say, 0 to 30% throttle. So 30 to 100% is fairly linear, but 0 to 30% is not very linear. So we'll go into that in a little bit, but I think this is what I'm going to do here. I'm going to go ahead and weld this up, bolt it all together, and then we'll set up the linkage for the actuator. Okay, so I've welded the mounting plate for the governor actuator to the pedestal here. So once this cools, I'm going to go ahead and bolt the actuator on and set it up on the engine so I can line up the linkages, or the linkage, and mark out where it has to be welded to the blanking plate. So we got the throttle lever here, and up there the governor actuator's lever. They line up pretty close. And you know what, I could probably, you see how that governor actuator's lever is really just a piece of stamped steel with a bend in it. I could probably flip that inside out, and then that would offset it over another, well, maybe 3/8 of an inch, make it line up perfectly. Even if you did have to have a little offset in the throttle linkage, it's not the end of the world, nothing to be ashamed of there. So, okay, I'm going to go ahead and mark that out where it is and weld it up. Here's the finished governor mount. I think it came out pretty nice. I added a couple extra gussets here on the side. I don't think vibration is going to be a real issue. This engine has a lot of mass, and I don't think there's any real dramatic vibration. Even though we're going to have quite a bit of weight in the form of that actuator mounted up top here, I don't think it's going to be a problem. So I'm going to go ahead and give this a coat of paint, and while it's drying, we'll move on. I think we'll put the mag pickup in. So I think I'm going to mount the mag pickup right somewhere in this area of the bell housing. What's nice is we've got this huge timing window here, and you can actually see the ring gear down there. That way, if somebody had a mind to, they could actually take a feeler gauge in here and set the gap between the tip of the mag pickup and the flywheel teeth with, high precision. But that's really not all that necessary. So, well, first thing we got to do is determine where on the bell housing we have to drill the hole to mount the mag pickup. We want it approximately in the center of the ring gear. The center of the width of the ring gear, I should say. And luckily on this engine, or fortunately on this engine, we've got a second position for a starter motor here in the bell housing, so we can clearly see the ring gear. And it's very wide. It's approximately 1 inch wide. Big gear. So from that, and in this area, we know, okay, so we got a 1 inch wide ring gear, and it's approximately what, 1, 2, 3 inches from the far edge of the ring gear to this machined face here of the bell housing. So that, we'll put it right in the center of the ring gear, so we need about 2.5 inches in from this machined face. And the nice thing is this machined face right here continues, well, it doesn't quite continue, there's a gap, but that machined face is where it mates up to the engine block, and you can see that that parting line right there is at the same height up from the casting. So we can use this parting line, bring a straight edge up, and then measure over on the bell housing to locate the mag pickup position. So let's go ahead and do that. We're just going to use a simple old combination square, my little scale here. We'll set, there's actually not, this face here is not machined, it's just rough cast, but it's pretty flat. So I'm just going to set the very edge of the square on that casting and really pretty much just line this up by eye. Just looking down the length of the rule there. It's cold in here, you can see my breath. And then set the scale right on the square. Get it approximately in the center of that window, right where the pointer is. Okay. Looks good. You take that away. And 1, 2.5. So that's where we're drilling for the mag pickup. So let's go ahead and drill this hole. So I've got the mark here, center punched, and I'm going to use this is a magnetic base for a dial indicator. I'm going to use it on this fairly flat surface here, and set the rod here approximately in line with the hole. Just leave that right there, and we're going to freehand drill this. I got a small bit here just to pilot drill it. This is just to give me something to line the drill up with, to kind of keep the bit square and pointed directly at the center line of the crankshaft. You don't want to have it drilled like this or like this. You don't want to have the mag pickup meeting the OD of the flywheel, which would be the OD that's formed by the teeth. You don't want to have that mag pickup meeting that at an angle other than 0, because if you do, you're never going to get it set right. So we're just going to set it there, get it lined up. Okay, we got our little divot started. One thing I want to mention, we have a large gap between the inside of the bell housing and the ring gear. It's probably, maybe 1.5 inches or so. So I don't have any kind of stop on the drill. So I I think when I break through the other side, I'll be able to catch it before the bit actually runs into the teeth. But if you didn't have much of a gap, which some engines you don't, you're going to want to put like a stop collar on the drill itself, so that when you break through, you don't run your bit right into the teeth of the ring gear. So let's go ahead and drill this on through. Okay. That looks pretty darn square to me. All right, we'll follow that up with the tap drill, which is an R, I believe. We're drilling for 3/8 24 thread size. So I'll put this back on just to help keep it lined up, even though we got a pilot hole for the drill to follow. Now where the heck's the bit at? Oh, there it is. Okay. Get that lined up. All right. Oh, that base isn't quite on there. I don't have a lot of clearance between the base and the side of the drill. I probably don't really need it right now, but it's a little peace of mind. All right, feels like it's getting ready to break through there. I'm going to take this away. Yep, we're just about ready to break through. There you go. That's probably about a 1/2 inch thick, well, maybe not quite a half. Maybe 7/16 inch thick bell housing. So we'll have plenty of meat there for threading. We'll put the base back up here. Well, that's not, well, yeah, we could put the base back up over here just as a point of reference. Let me bring my little chair over here. Yeah, we're still recording. This will help me get it started straight. Okay. Feels like we're started now. No, still a little wobbly. Okay. So I'm going to back that out and go get a little bit of grease and put some grease on the tap to kind of hold the chips there. I don't want to make, especially with an iron bell housing here, we don't want to make too much grit and dirt. It's not that big of a deal, but the thing is, any little magnetic chips tend to collect on the tip of that mag pickup because it is a magnet, and that can disrupt the signal that mag pickup generates back to the governor controller. Plus, we don't want a bunch of conductive filings spinning around in a generator. Even though the airflow of the generator is coming from the back out the sides, it's not like going to get sucked through the generator. It's just good practice to try to avoid that. So let me go get some grease. I wasn't so worried about the filings from drilling, because the nature of the helix of the drill kind of brought most of it out. And the grease here is just going to help to hold those filings. Take this away now. I think we're started nice and straight. All right, we're through. See, that grease kind of held all the chips on the tip of the tap there. Yeah, the tip of the tap, that's all. Okay, let's give a mag pickup a test fit. Make sure I didn't thread it wrong. Thread size. Yep, it's going right in there. So before we actually install the mag pickup, we've got to create a bit of a flat surface here for the lock nut to sit squarely up against, because the casting's a bit rough. So I'm just going to take a little cookie wheel and a die grinder and kind of flatten this area out, and then we can install the mag pickup. Well, I threaded the mag pickup in most of the way, and can you see what I meant about kind of creating a flat spot for that nut to seat on? Okay, so now we got the mag pickup running most of the way. You can see the tip of it in there. I've turned the engine so that I have a tooth, a flywheel tooth, right under the bottom of the mag pickup. So at this point, all you have to do is thread it in there until it contacts that tooth. Kind of makes it awkward having this wire on there. Okay, so it's right up against the tooth now. Let me take this light out of here. And you want to contact that tooth and go approximately 1/2 to 3/4 of a turn out. So I'm going to go between 1/2 and 3/4 there. And just use the lock nut and lock it down. You got to be careful. Sometimes the sensor itself will want to rotate on you. Let me grab a pair of pliers just so I can grip it nice and tight. And just snug the lock nut up. So that's all there is to setting them. Now in some situations, if you have a mag pickup that's not generating a strong enough signal, you can run it in a little bit closer. I wouldn't go any closer than, well, maybe 3/8 of a turn out. 1/2 an inch is really about as close as I ever want to get them, or 1/2 of a turn rather, not 1/2 an inch. 1/2 a turn out from fully seated. So, all right, well, the mag pickup's in, so let's move on to the actuator. We'll put that together and make up the linkage. Okay, so here's the actuator mounted up. I went ahead and I painted the pedestal Onan green. Figured it was only right. So yeah, mounted up. I got my linkage made and assembled there. So let's talk about that. Let me set you up on the tripod here. Now I mentioned before that when you're setting up a electronic governor, there we go, on like a gaseous fueled unit like this, or anything that uses this style of throttle, like a butterfly throttle, you want the linkage set up in a non-linear orientation, because butterfly throttles are not linear. And what I mean by that is, for a certain degree change in the throttle position, degrees of rotation, let's say from 10 to 20 degrees of rotation, you get a certain horsepower increase. Well, between 80 and 90% of rotation, you get a different amount of horsepower increase or change. So it's kind of hard to describe. There's some good publications online about the geometry of the throttle, of a throttle butterfly, and flow rates, mass flow rates. It's kind of complicated. But when you're installing a governor like this, you want to pretty much set it up so that when the actuator is at near full travel, you want the throttle at wide open. So what I'm getting at is, in this area of travel, you want pretty much a 1-to-1 ratio of movement. So in the higher throttle, or the higher RPM, or the higher throttle band, you want about a 1-to-1 ratio between actuator travel and throttle travel. But down low in the idle area, you want a greater amount of throttle travel per amount of actuator travel. So can you see that clearly for a very small movement here, at this point, I'm getting a fairly large movement here at the throttle. So again, it's kind of hard to describe. There's a lot of, there's a lot of publications online about this. So that's really all I'm going to say about it. Other than when you're doing a diesel setup, most of the time diesel injection systems, diesel pumps, are linear. So from no fuel to full fuel, all the divisions are equal. You get an equal rate of fueling increase, whereas you don't with a throttle, except for like the Cummins PT pump. Cummins PT pump is more like a throttle body than it is a diesel injection pump. Before we move on, I want to say one other thing. So the manufacturers of these actuators recommend that you never operate them to their full stroke. So let's say this, well, I'll show you. Let's not just say, I'll show you. So let me disconnect this side over here. Okay. So here's the stroke of the actuator from one stop to the other stop. Here's a stroke of the throttle from one stop to the other stop. The manufacturers want you to use the stop of the throttle. So you want to go from stop to stop, not from stop to stop. You understand kind of it? You never want to run these things to their complete maximum range. So when I'm at full throttle, I want the actuator to travel a little bit past what the full throttle would be. You can see we're probably about a ½ an inch past the maximum range of the actual butterfly. So when it's down toward idle, we're still a little bit past. I actually have to move the actuator back to get it to line up. So you want to use the throttle stops, not the actuator stops. Okay, so I want to talk real briefly about the carburetor here. So I've removed the 5 screws to this cover plate, and when you take them off, pretty much you have a spring, don't lose it, and the diaphragm. And that's really all there is to these. There is an adjustment up here, which is your full load. Let me take you off the tripod here. Your full load adjustment. come over here. So really the only time you mess with this, see it's got a R for rich and an L for lean there. The only time you adjust this is when you're setting the carburetor up initially, and you do it when the engine is under its full rated load. And all this is another butterfly in the line of the pipe here, just to kind of restrict the fuel flow. But really, they don't. It doesn't do much for single speed application engines like this. You pretty much set it once, and then you don't ever have to touch it again. You've got one other adjustment here, which is pretty much just like your idle air control, more or less. So when you're at low speed, this controls the amount of air that goes into the engine. So we're not really going to talk about that either, because for single speed applications like this, you don't really have an idle per se. You're always running at a fixed speed. So this is always closed or all the way seated. So let me go draw a little diagram of how this is all set up. Here's a little diagram I drew. So I hope it's easy enough to understand. But here's the diaphragm. All right. So you can see that there's a little cone right in the center here. That's this little cone you see here. This flange area here represents a cross-section view of this block right here. And then little curved areas are the diaphragm, and this big cap is the outside cap to the carburetor. So when the thing is all assembled, we got fresh air coming from the air filter here, which when the engine's not running only has access to the diaphragm here, to the inner surface, because this point right here and this point right here are seals that sit right on this ring. So there's a ring that sits where my fingers are at, that this spring pushes the diaphragm up against to seal it. It also seals the gas off right here, because this surface here and this surface are right about the same height. So all of those areas seal at the same time. Now you'll notice we've got 4 holes right here. These 4 holes lead to the other side of the diaphragm. Now the other side of this cover, this block, is completely sealed from the atmosphere. So when the engine is called to run and it begins cranking, you've got 2 engine here. This is the throttle, or the intake going into the intake manifold. So a negative pressure is developed here as the engine is turning over. That negative pressure is delivered through the holes here, through these holes, to this side of the diaphragm. So now you've got a negative pressure here in this area and a negative pressure in this area. Well, because the surface area of the diaphragm is significantly greater than the surface area inside this ring, the atmosphere pushes the diaphragm up. Move this spring out of here. So the diaphragm actually moves up like that, which opens the seal for the atmospheric air and the gas at the same time. So the atmospheric air can now go past this seal down to the engine, and the gas can pass this seal and come out around here and mix with the atmospheric air. Now that cone has a couple cutouts in it. Turn the light on here. See the cutouts there? Well, the shape of that cone and the size and the depth of those cutouts determine the amount of fuel that comes in mixes with the air per a given movement of the diaphragm. So there's actually, what is this? This is a V1-12 part number. So that just defines the shape of the cone. Now, different engines vary. So I think there's a V1-12, a V1-14, and the shapes of the cones are just a little bit different, just for whatever air-fuel ratio that the thing is spec'd out for. So, and this exact thing happens on both sides of that carburetor body. So you got 2 diaphragms, 2 sets of springs, sealing area. So we got atmospheric air comes in here and goes around the outer seal. This ring here is this outer seal. The inner ring here is the inner seal right there. So the little cone sits in that hole. That's gas that's coming through this pipe down through here and exits right there. And then this inner hole goes straight down into the engine. So that's all I'm going to say about that. Hopefully it was clear enough. If you have any other questions, post it in the comments and I'll try to answer it as best I can. Mounted up the governor controller inside here. Not much to it really. You got battery positive, battery negative, the output to the actuator, which is not polarity sensitive, it's just 2 wires, and the mag pickup input. So typically, well, at least in this case, the mag pickup is a shielded cable, and we've got the shield going to the negative input, so that's technically tied to ground, and then this would be the signal input. So not all controllers are like that, but most of them are. Some of them want you to just take the shield to actual chassis ground because the inputs are isolated. So everything's wired up temporary. This is just lamp wire. Of course, I wouldn't leave that. And we're just going to clip it onto the battery when we're ready to set up the governor. So that's pretty much it. I got to haul it outside and we'll fire it up. Okay, we got the generator pulled outside and hooked up to gas. We got a battery hooked up to it. So I've already had the thing running to warm it up. Now the first thing we got to do is crank the engine over and see what the output of the mag pickup is at cranking speed. So the throttle, I guess if this wasn't obvious earlier, I'll say it now, the throttle rests closed. So the engine typically, in order to get it to fire, needs the throttle opened to get, just to get it to kick off and start ramping up to speed. Well, the governor will not open the throttle until it sees a speed signal. Now, while the engine's running, the output from this mag pickup is probably going to be in the neighborhood of 20 volts, which is plenty of signal strength. However, at cranking speed, it's going to be much, much lower. Really, the bare minimum is about 3 volts. Anything less than that, well, you probably want to change your mag pickup out to something that will generate a better signal. This one is a 600 ohm mag pickup. 1000 ohm mag pickup might be a little bit better if we get a low signal, but I think we should be okay with this. So let's go ahead. I'm going to crank it over. Let's see, I got the gas off over there, right? So I'm going to crank the engine over with no ignition and no gas, and I'm going to check the mag pickup voltage. Let me zoom on in the controller here. Okay. All right, the gas is off. Ignition's off. So set the meter to AC voltage. Can you see that? Yeah, I think you can. Okay. And we're going to read the input on the mag pickup terminals. Okay, let's crank the engine. Huh, wow, that's pretty low. It jumps up to 3, but it really stays between 1 and 2. So that's pretty much on the edge of acceptability. Really, it's unacceptable if this was installed in the field. So I'll have to look into getting a different mag pickup. So now that we know our mag pickup output at cranking speed, let's just go over the adjustments here on the governor controller real quick. So at the top here we got 2 dip switches and what they do over here. So dip switch, you want to one you want to set off for diesel and on for gas. That just kind of controls the profile that the unit will govern to. And then there's 3 different types of actuators. The 8000 series actuator, which is what we have, and the 82 or the 8400. So we want to set dip switch 2 off for the 8000 series actuator. So we got them set right. We got a droop pot. We're going to set that to 0. Droop really is only used when you're paralleling engines. The slave units will have a certain amount of droop set on them, so the master unit will always keep the frequency. We got an I, that's integer or integral, and then a gain pot. So these two pots here kind of almost do the same thing, but from different perspectives. Think of it like that. So the gain is how quickly the controller will respond to load changes, and the integral kind of bucks the gain to help even it out. Think of this one as like a stability adjustment. And then we have a speed pot down here. This is like a 10-turn, 10-turn trim pot. When you're first adjusting these governors, you want to run that all the way counterclockwise, or pretty much to 0 speed. You'll get to a point where you'll hear it click on it internally, so you know you're at the end of its travel. So I've already got that set to 0. So let's go ahead and start the generator, or start the engine up. And I'll put my meter on the output voltmeter so we can get an idea of what the engine frequency, or the generator frequency is. We're ready to start the engine. Now, I think I misspoke earlier. The first thing we're going to do is provide power to the governor. Because the control system isn't set up and everything, it's not permanently wired, I'm going to manually connect the governor. We want to do that first because the first thing that's going to happen is the actuator is going to jump to full fuel and then return to idle. So that's just the controller doing a bit of a self-test. It's going to power that. So I'm going to go over and connect that and zoom you in here on the throttle linkage. All right, let me go connect that up. Okay, so you saw that little jump. Let me zoom you on back out here and get you to a point where you're going to be able to see what exactly is going on. Bring you down a little bit. Okay, now I'm going to go and start the engine. Okay, so now the engine's running at pretty much its idle speed because the governor speed is set to essentially 0. So the throttle is just kind of floating right now, but because the actuator has a spring return, it's spring returning to idle. So sitting here with no governor activity, we're at 43 hertz. So I'm going to go ahead, let me bring you in a little closer here. I'm going to go in and bring the speed pot up and get her to about 61 hertz. response is extremely laggy or lazy right now because I have the gain and the integral turned all the way to 0. I'll go over the engine and we'll show you what that means. You're not going to be able to hear me, so I'm not going to speak. Could you kind of see how when I manipulated the throttle, especially when I slowed the engine down, the Governor Actuator slowly brought the speed back up. And that's okay. That's, well, it's not okay really. In a real world situation with a load on it, if you had a large piece of equipment start up, the engine speed would fall dramatically before the governor would catch the engine back up, essentially, before the throttle would ramp open. So we're going to turn the gain up a little bit and see if we can get better response. Set the gain to 50. Let's see what the throttle does now. A little bit better, still not very good, especially you'll notice that when the governor drug the throttle wide open, the engine speed actually fell. And that is due to the fact that my gas pressure is literally falling to 0 when that throttle cracks open. So I don't think we're going to be able to get the thing adjusted perfectly on my house supply. We're going to have to wait until we bring it into the shop and get the big gas feed hooked up to it for when we load bank it. But let's see if we can adjust the integral and get it a little bit better. really can't get it dialed in just because the engine does not have very good response, being that it's literally only running on fumes right now. I think we're going to have to call it quits for right now. I'm not going to be able to get it dialed in here at the house. I'm going to go ahead and disconnect the governor, and I'm going to disconnect my wireless mic and just use the camera mic so you can get a better idea how this engine sounds. Well, I hope the sound came out okay there. I know the last time we ran this thing, the wireless mic was kind of clipping the audio, so you were just kind of getting static. Hopefully you can get an idea of how this engine sounds. It has a pretty throaty sound to it, but especially when I throttle it up, you can tell it's cutting out because it's not getting any fuel. The residential gas meter cannot supply this thing. Alright. Well, let's go shut it down and we'll recap here. Yeah, still got that number 6 exhaust valve. That's a shame. Let's kill the ignition here. Alright, well, that's about the end of this video. So, we did get a successful governor installation. However, we cannot test it fully here with my meager fuel supply. So the next step with this thing is to put the air filter back on, put all the covers back on, and haul it into the shop at work where we got the big 2-inch gas feed for it, and hook it up to a load bank and see what it can really do. So thanks for watching. I know it was a long video. I appreciate you sticking with it, and stay tuned for more.